Hello and welcome. We are starting today a new session, sequence and series. To motivate, I will try to give one example. Suppose that a ball, so this is a ball. Suppose that this is thrown downwards. Suppose that from a height, this is thrown downwards. And now suppose that it hits the ground and all these things, suppose it happens in 10 seconds. Now suppose that the ball bounces upward. Now it is going upward. So the upward journey is here. Now suppose that for bouncing upwards it takes 10 by 3 seconds. Now again suppose that it is going downward. Of course it has to go downward. So it bounced upward. It is now coming downward. So the ball reached up to here. The ball is now here. And suppose that this time it is taking less time, 10 by 3 square, because it's coming downward. And now suppose that it is bouncing again upward. With a shorter distance. It is now bouncing upward with a shorter distance and probably shorter time also. So the ball is bounced, so 10 by 3 raised to 3 seconds. And suppose that this goes on like this. So we have a ball that is thrown downwards vertically from some height. It hits the ground, it bounces up, and initially it took 10 seconds for reaching the ground, and after that it is taking 10 by 3 seconds for going up, and after that it's taking 10 by 3 square seconds for again coming down. And of course this seconds is coming down, it's becoming smaller and smaller. Now after that it's taking again 10 by 3 cube seconds, and it keeps on going like that. So what happens is that in each and every step for bouncing, rebouncing, so the time taken is 10, then 10 by 3, and then 10 by 3 square, then 10 by 3 cube, etc. And if you observe carefully, we can see that the time taken is actually, it's becoming closer and closer to 0, or in some sense it's approaching 0. Therefore the question is this: so within how much time the ball will come into rest? So it will permanently lie on the ground within how much time? So for finding the time taken by the ball, we need to consider all the times that it took for bouncing upward and downward, and then we have to add all these things. So the time taken for to lie on ground permanently, this is nothing but this is equal to 10 plus 10 by 3 plus 10 by 3 square plus 10 by 3 cube plus etc. And if we have okay, 10 is common here, 1 plus 1 by 3 plus 1 by 3 square plus etc. And if you are familiar with the geometric series concept, you can identify that this is a geometric series, and this 1 by 3 is something known as common ratio, and 1 plus 1 by 3 plus 1 by 3 square plus etc. going up to infinity. And if a is the static time, here the static time is 1, and solution is 1 by a by 1 minus r, therefore 10 by 1 minus 1 by 3. This is nothing but equal to 10 into 1 by 2 by 3, that is equal to 30 by 2 or 15 seconds. So the total taken by the ball to lie on the ground permanently is 15 seconds according to our computation. See that we have added actually infinitely many real numbers here, and we are finally arriving at a finite real number. The summation 10 plus 10 by 3 plus 10 by 3 square etc. is known as a series in real analysis. This is an infinite series, but we call it as a series, and the terms 10, 10 by 3, 10 by 3 square etc. they are known as they together known as a sequence in real analysis. So the topic that we are going to start discussion from today is sequences and series, and this is probably a motivating example for learning sequences and series. We are initially going to define a sequence. A sequence, informally speaking, a sequence in a real sequence, in fact, it's an ordered set of real numbers. Informally, this is an informal definition. Sequence is an ordered set or ordered list, that's better, of real numbers. Like the ordered list, say x1 is the first number, x2, x3, etc. But if you carefully look at this is nothing but x1 is nothing but x of 1, x2 is nothing but x of 2, this is x of 3, etc. So 1, 2, 3, etc. are appearing in this expression, in this notation. Therefore, this is nothing but, this is actually the image of a function from the set of all natural numbers to the set of all real numbers. So formally, function is, even though we identify a sequence to be a set of numbers, the formal definition is that it is actually a function from natural numbers to the set of all real numbers. So this is the formal definition. A sequence in R, or a real number sequence, is a function x from n to R. Of course, instead of x we can use y, we can use f, we can use any symbol. We usually denote sequence. One notation is that x1, x2, x3, etc. But of course, this is not very clear that what is going to be the nth term. Therefore, we must try to avoid this notation as much as possible. Second notation is to define xn equal to something, and we usually denote the sequence like this. These are two ways. So this is actually the way in which we define xn. This is one notation, and sometimes we use this notation also, but we will be most probably sticking to this notation. These are the notations of sequences. Now we will have a few examples. Examples we can have plenty. 1, 2, 3, etc. Therefore, we are defining the nth term to be equal to just n for all n in natural numbers. Remember that to define a sequence without any ambiguity, we need to clearly say that what exactly the nth term is going to be. Instead of that, if you simply write that 2, 3, 4, etc., it is not very clear that what is going to be the next term. So most of the times it is not preferable to use that notation, this dot 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 etc. notation, but instead of that we should define sequence by specifying its nth term. So another example is 1, 1 by 2, 1 by 3, etc. and therefore the nth term is nothing but 1 by n for n natural number. This is another example. Now there is another way of defining sequence x's, which is, and another thing is that even though we have formally defined the sequence to be a function from n to r, so therefore the images are going to be x1, x2, x3, etc. Sometimes it may happen that we start with x0 and then go to x1, x2, etc. So don't get confused. We may sometimes use x0, x1, x2, etc. also, and in that case we may probably think that the sequence is actually a function from the set of all whole numbers to the set of all real numbers, or from natural numbers to real numbers. So there is no need of confusion. We may use both 1 as well as 0 as the starting index. So next one, we are defining the following way: x0 equal to 1, we are defining x1 equal to 1 and xn plus 1 equal to xn plus xn minus 1 for all n equal to, for n equal to 1, 2, etc. Therefore, what are the other terms? x2 is nothing but x1 plus x0, that is equal to 2. x3 is nothing but x2 plus x1, that is nothing but equal to 2 plus 1, that is 3. Next term is going to be here. Next term is x4 equal to x3 plus x2, that is equal to 3 plus 2, 5. Now x5 is equal to x4 plus x3, that is 5 plus 3, that is 8, and go on like that. And this sequence is known as Fibonacci sequence, and the numbers x0, x1, x2, etc. are known as Fibonacci numbers. So this is a very interesting example, and this has a lot of applications also in several branches of mathematics. Now we will see another example. And one more thing, the relation that we define here, the n plus 1 term in terms of 2 of the previous terms, this relation we define here is known as a recurrence relation, or a recursive. Okay, recurrence relation is the best thing, not recursive. Okay, let it be like that. So we may define sequence like that also. Next example is 1, 1, 1, 1, etc. That is xn equal to 1 for all n. Such sequences where all the terms are same, such sequences are known as xn equal to a for all n. A, some real number that is fixed. If xn is equal to a for all n, the sequence xn is known as a constant sequence. This is another example. Therefore, it means that in a sequence, numbers may repeat. Another one, 1, 2, 1, 2, etc. That is xn equal to 1 if n odd, 2 if n even. This is another way of defining sequences. So these are all simple examples of sequences, and note that here in the first sequence listed here 1, 1, 1, etc. there is only one unique distinct element in the sequence, and here there are only two elements, and in the previous examples all the terms were distinct, so anything can happen. So it can happen that there are only finitely many terms. It can happen that there are infinitely many terms, in the sense that finitely many distinct terms in the set of all elements in that sequence, or infinitely many distinct terms in the set of all elements from that sequence. Now, if we look at one of the previous examples, we have seen that the sequence, one observation is the following. Consider the sequence 1, 1 by 2, 1 by 3, etc., which is defined by xn equal to 1 by n. And if we look at this carefully, we know that 1 by 2 has a decimal value equal to 0.5, and of course after that 1 by 10 comes. Okay, we'll look at the powers of 10. 1 by 10 is 0.1, 1 by 100 is 0.01, after that 1 by 1000 is there, 0.001, and 0.0001, etc. And we can see that the size of the elements it keeps on increasing, and the elements are actually when it moves towards the end, the size becomes closer to zero, or in some other way, these terms are approaching zero. So, but what is meant by saying that approaching zero? So that is not very clear. That what is meant by saying that some numbers, as we go on along these numbers, the numbers are approaching zero means what? So we will try to make that clear. So we have a definition here. A sequence xn converges to x belongs to R if for any epsilon greater than 0, there exists natural number such that after this natural number, all the xn's are at a distance of less than epsilon from x. That means, pictorially we can represent it like this. Suppose that we have x lying somewhere here. This is the real line, and suppose that we have x here. Suppose that here we have this is xn minus x less than epsilon, means that at a distance of epsilon from to the left and right of. So this is x minus epsilon, this is x plus epsilon. So the sequence may have terms appearing here, here, etc. And after some time, what happens is that all the terms are here. That means this is xn minus 1, this is xn, this is xn plus 1, etc. That means that if capital N, suppose that it is 10, then x11 onwards. So for example, if n equal to 10, then x1, x10 minus x less than epsilon, x11 minus x less than epsilon, etc. Going on like that, x20 minus x less than epsilon. So if we have n equal to 10 here, then all these inequalities must be satisfied. So that means that all the terms from the 10th term onwards will be at a distance of less than epsilon from x, or they are close to x by a maximum distance of epsilon. So the sequence, the terms in the sequence is close to the number x by a distance of maximum epsilon. That is what's meant by saying that the sequence xn converges. So another important thing to observe is that this is for any epsilon greater than. So therefore, if we change this epsilon, we may have to find another n. So we will clarify these things when using another example. We'll clarify it using an example here. So consider the sequence. One, 1 by 2, 1 by 3, etc. Suppose epsilon is given to be equal to 0.25. So the question is to find n such that if n is greater than or equal to n, then xn minus x equal to 0. xn minus 0 is less than epsilon. That is, xn minus 0 is nothing but xn. xn is less than 0.25. So we need to find capital M such that after that capital M, after or equal to that capital M, all the terms are going to be at a distance of less than 0.25 from 0, or all the terms are less than 0.25. So How do we find it? We know that 0.1 is less than 0.25, but 0.1 is nothing but 1 by 10. Now, what about 1 by 11? So 1 by 10 is less than epsilon. Modulus is not necessary because all numbers are positive. 1 by 11, that is less than 1 by 10, that is less than epsilon. Therefore, if n is greater than or equal to 10, then 1 by xn equal to 1 by n is going to be less than epsilon. So we can choose n to be equal to 10. Of course, we can also choose n to be 100, because we know that if n is equal to 100, the term is going to be 1 by 100. 1 by 100 is, of course, it's less than 0.25. 1 by 100. So we are being asked to find some n. The observation is the following: the n we are finding, first thing is that it depends on epsilon. See, in the previous example, here we had epsilon equal to 0.25, and therefore we could take capital N to be equal to 1 by 10. This is first observation, because otherwise let epsilon equal to 0.01. Therefore, n equal to 10. This will not work. Therefore, epsilon equal to 0.001. This is equal to 0.01. This is equal to 1 by 100. Therefore, we may choose n to be equal to 101, because you know that 1 by 101 is less than 1 by 100, and after that 1 by 102 everything will be less. Therefore, n depends on 101. That's very important. So we may even write n of epsilon instead of simply writing n to show the dependence of, that is, n depends on epsilon, or n is a function of epsilon. That is the most correct word to use. N is a function of epsilon. The next thing is observation 2, that the n we find need not be the least, such that xn minus x less than epsilon if n greater than or equal to n. We don't have to find the least such possible n. We can find any n, and from that particular n onwards, this xn must satisfy this inequality. That is the only thing. So we don't have to look for, we don't have to take the strain of searching for the smallest possible n or anything like that. That is not necessary. Now we have another example. So the question is to find n such that 1 by 3 raised to n 1 by 3 raised to n is minus 0 is less than 0.005 whenever n greater than or equal to n. So here we are supposed to find the term from where onwards this 1 by the terms in that sequence is going to be less than 0.005. In fact, the difference of the term with 0 is less than 0.005. So this is, in this case also, remember that we don't have to find a strict n, in the sense that the least possible n satisfying this condition. We can find any n. So this can be done in many ways, but maybe this is one possible way. We know that 1 by 3 cube is less than 1 by 10. It is always easy to compare using the negative powers of 10, so that is easy to identify. So we need it to be less than 0.005. 0.005 is nothing but this is 5 by 1000, and therefore this is going to be greater than 1 by 1000. Therefore, if we bring 1 by 1000 here, this is going to be less than. So this is less than. Okay, we need 1000 here. So 1 by. Okay, we already got that. So this is less than 10. Therefore, 1 by 3 cube. The whole cube is less than 1 by 10 cube, which is 1000. This is 1 by 3 to the power 9, that is less than 1 by 1000, that is less than 0.005. So we may choose n to be equal to 9, because we know that from 9 onwards it's going to be less than 0.005. These are two examples where we try to locate n depending upon epsilon. Remember that there are two observations regarding this epsilon. One observation is that the n we are finding always depends on epsilon. The second observation is that the n we are finding need not be the least n, and maybe because of that we can have a third observation also. The n we are finding is never going to be unique. And with this we are stopping our initial introduction about sequences. Thank you.